Hello, shall I start?
Yes, sir, you can start.
Yes. Let me start, first of all, by thanking the organizers very much for this opportunity to speak at the birthday conference of Professor Dani, who's had so much influence on so many aspects of dynamics. I'm really very sorry that I was not able to travel to participate in person, but in terms of the date, this has proved to be absolutely impossible. But I still am very grateful for this opportunity. And I would like to talk today about, about the entropy theory of non-amenable groups. I've been interested in the dynamics of non-amenable groups for quite some time. Ergodic theory for non-amenable groups has a lot of surprises in it, and it evolved in all sorts of interesting directions. And the story of non-amenable entropy theory is really quite remarkable, and it has been completely revolutionized in the last decade. And what I would like to start with is give an introduction to some of the developments there from my own personal perspective, developments that have been initiated by Lewis Bowen and also continued by other people, including Brandon Seward, whose work we will emphasize. And I should mention that the talk is based on joint work with Felix Pogorzelski from Leipzig University. So the plan is to talk about the entropy of general group actions with some basic definitions, then to mention the classical theory of amenable groups and the convergence of information functions, then to mention briefly on the way to entropy theory beyond amenable groups, one of the main obstructions of this that this theory had to cross, and the remarkable and revolutionary development by Lewis Bowen of the f-invariant, and subsequently to that, Seward's definition of Rokhlin entropy. And then I would like to mention Seward's inequality and the definition of finitary entropy. And only in the end, I will explain our approach. We will restrict to negatively curved groups and define a certain notion of orbital entropy, which will provide us with an analog of the Shannon-McMillan-Breiman theorem along almost geodesics. Okay, so about the basic definitions, let X be a probability space and let P be a partition of X to a disjoint countable union of positive measure sets. The Shannon entropy of the partition P is defined in the usual way, minus sigma mu log mu. And the information function of the partition is defined by the function I P of X is minus log of the measure of Px, where Px is the unique atom of the partition P containing X. These are two completely standard definitions of entropy theory. Note that the Shannon entropy of P is the space average of the information function of the partition. HP is simply the integral over X of IPX d mu. Now, we would like to study the dynamics of partitions, the dynamic of partitions in measure-preserving systems. So the join of two partitions, P and Q, consists of the positive measure sets in the set of intersections, P, V, Q, which is A intersect B, such that A is in P and B is in Q. And the join, of course, the entropy, of course, is join subadditive. Age of P join Q is less than or equal than HP plus HQ. Now we consider a probability measure preserving action of a countable group gamma on the probability space X mu. And for a measure preserving transformation G from X to X, GP is the translate of the partition P, the set of, with partition sets GA such that A is in P. Now, P is called a generating partition if the only gamma invariant sigma algebra containing it is the full sigma algebra Bx. This is also a standard definition in entropy theory, and it was used extensively already in the early days, close to the definition by Kolmogorov-Sinai of classical entropy, but it assumes a huge part of the story that we're about to discuss. And now, what do we mean by the dynamics of partitions? So let Fn be a sequence of finite non-empty sets in gamma. And Pfn is defined to be the joint refinement of all the partitions Gp, where G is an element of Fn. These are called the successive refinements of P. And as Fn gets larger, we get a finer and finer partition. The sets we should expect to have measure which decays to zero. And so we are basically dividing the space to finer and finer pieces. Of course, this is the most direct and obvious generalization of the classical notion, where Fn is simply an interval of length n from 0 to n in Z. So this generalization is very natural. Now we would like to consider convergence of information or of entropies. So one basic question is, does the sequence of normalized Shannon entropies of the refined partitions Pfn converge? So we look at the Shannon entropy of the partition P refined by Fn, and we divide by the number of elements in Fn, and we wonder whether this sequence of entropies converge. A finer, much finer question is the question of, does the sequence of normalized information functions of the refined partitions Pfn, where now we take the function I Pfnx and divide it by the number of elements in Fn, does this function converge pointwise almost surely? And once again, these questions are really very direct generalization of the classical notion of entropy for actions of a single transformations, namely actions of the group Z. Now, the classical discussion of entropy theory was at first, well, for many years restricted to the theory of, to the case of amenable groups. And so recall that a sequence Fn in gamma is said to have the property of asymptotic invariance under left translations if when you translate Fn by some element G in gamma, and you compare it to Fn and divide by the size of Fn, then the limit of this expression is 1 for every G in gamma, meaning that for any given specific element G, the sets Fn eventually become asymptotically invariant under translation by G. And a countable group admitting a sequence of sets Fn with this property is an amenable group, as noted by Follner. And the sets Fn, of course, we can view them as being a generalization of intervals in the group gamma equals Z. The larger and longer and longer intervals in the group Z obviously have this property of asymptotic invariance, and so such a sequence in a general group gamma is an emulation of these intervals. This is a very powerful property, and it has been used extensively in ergodic theory and entropy theory. And now assume gamma is amenable and acts ergodically on a probability space, and that Fn are in fact asymptotically invariant. Then we do have convergence of entropy. the sequence of normalized Shannon entropies, 1 over the size of Fn, the entropy of the partition P refined over Fn, converges to a limit, HPFN, called the entropy of the partition. And the proof, which goes back quite a while, is based on a general subadditive convergence theorem for amenable groups, generalizing the corresponding fact for subadditive sequences, namely for numerical sequences AN such that AN plus M is less than or equal than AN plus AM, which of course is a condition that implies that AN over N converges. And suitable notions of subadditivity connected to amenability were developed and utilized by Kiefer and Emerson in the 70s, Ornstein-Weiss and Olanier in the 80s, with the most general form given by Lindstrauss and Weiss in the year 2000. This is a very classical topic. Once again, let me notice that here we only need asymptotic invariance, but then again, we only require that the sequence of entropies will converge. The Kolmogorov-Sinai entropy of an action of an amenable group is then defined to be the supremum of this notion of entropy, HPFN, where P is a finite partition of X, which once again is a very direct generalization of the classical definition for a single transformation. And it is a fundamental fact that this is indeed an isomorphism invariant of the group action depending only on X, and does not depend on the asymptotically invariant sequence chosen to define it. And we emphasize that the definition of the Kolmogorov-Sinai entropy employs the supremum over finite partitions. One consequence of that is that if phi from x mu to x prime u prime is a measure-preserving equivariant factor map, every partition of x prime can be lifted to a partition of x. I guess that's a typo. And so, because you take a supremum on a larger set, the Kolmogorov-Sinai of the cover X, it has to be greater or equal than the Kolmogorov-Sinai entropy of the factor. So the Kolmogorov-Sinai entropy is monotone. The larger the cover, the larger the entropy. That is a completely inescapable fact because you take the supremum over a larger set. So there's just no way to avoid it. Okay. Now, entropy equipartition, and sometimes also known as the Shannon-McMillan-Breiman theorem for amenable groups, once again, this is the statement that you have pointwise convergence. This is a much more demanding statement. Here we assume that the sequence Fn satisfies the stronger asymptotic invariance property of temperedness. Again, recall that PFN-X is the unique atom of the partition PFN containing X. And the Shannon-McMillan-Breiman theorem asserts that the sequence of normalized information functions associated with the refined partitions IPFN, the log of the measure of the atom PFNX divided by the size of Fn converges for almost every X to that same entropy HPFN of the partition P that was defined before. Okay, so this is a pointwise convergence theorem. This result that has just been stated for the case of tempered sequences of tempered asymptotically invariant sequences is due to Lindenstrauss. And it's the culmination of a long sequence of work extending a result of Kiefer from 75, Ornstein-Weiss in 83 for a more stringent condition of almost invariance, and also Olanier. A different proof of this theorem was given by Bengaluru in 2004. And so this result establishes asymptotic entropy equipartition for ergodic dynamical systems. This means that if you refine a partition, then what you should expect after refining with a very large Fn is that most of the atoms have roughly the same measure or decays in roughly the same rate, and that rate is e to the minus the entropy of the dynamical system times n. That's the reason behind the statement of entropy equipartition. Note the terminology of entropy equipartition. So this is a very satisfactory state of affairs. There is a very robust and stable definition of entropy, and it has this convergence property, which is based on subadditivity. It also has a pointwise Shannon-McMillan-Breiman theorem establishing entropy equipartition. So this is a very nice state of affairs. And now, let's consider what, in some cases at least, is really the first example of a non-amenable group, although I don't know, maybe other people have other favorite examples, which is the case of the free group. And here we come to the Ornstein-Weiss example. So the question is whether entropy theory can be extended beyond amenable groups. And so for that, consider the following example that they constructed. Let X be Z2, namely 0, 1, space of two elements, to the power F2, namely all the functions from F2 taking two values, 0 and 1. This is the so-called Bernoulli action of F2. And we take mu to be simply the uniform product measure. This is, okay, maybe the simplest example of a probability space that F2 acts on. And X is a compact abelian group with Haar measure mu, and so is X times X with Haar measure mu times mu. And now Ornstein and Weiss define a map, capital Phi, from X to X cross X, mapping a function a function X to the pair XG minus XGA and XG minus XGB, which is certainly a well-defined map. And it can be shown that Phi is a continuous and surjective group homomorphisms. And it maps, as a result, Haar measure on X to Haar measure on X cross X. And its kernel is in fact just the two constant functions. It has a kernel with two elements. And furthermore, this is obvious from its definition, Phi is equivariant with respect to the left F2 actions on both spaces. So X times X is a factor of X. And this was constructed in the most explicit fashion. But any acceptable entropy theory should give the value log K for a uniform Bernoulli shift with K symbols. But here the factor space X times X has base space entropy log 4, while the cover has base space entropy log 2. And so, even for Bernoulli actions of free groups, such an entropy theory, if it actually exists, cannot be monotone. And that is an extremely sharp departure from the classical case. And it's such a radical departure that it led, I think, Ornstein and Weiss to suspect that actually you cannot have any meaningful entropy theory for free groups. But that turned out, and that's really quite a remarkable story and really a revolution in this subject, that turned out not to be the case. Entropy theory was revolutionized in 2009 by Lewis Bowen, who introduced the f-invariant, which he defined, a remarkable new isomorphism invariant for ergodic actions of free groups. And Bowen defines the following remarkable function. For a partition P of X, he considers capital F of P minus 3 of the Shannon entropy of P plus the Shannon entropy of P join the translate of P by A plus the Shannon entropy of P join the translate of P by B. Okay, this is not a function that everybody would immediately guess. And then Bowen defines the f-invariant little f of x mu, well, f2 or other actions, well, actually, yeah, x mu and f2 to be the infimum of the function capital F applied to the partition P refined by BR. BR is a word metric ball of radius R, and so PBR is a partition which is refined more and more. In fact, if you like, with exponentially many elements, the ball of radius R has roughly 3 to the R elements in it. But now here is the most remarkable insight of Bowen about this matter. He restricted this to P being a generating partition under F2. And so maybe one can work with this function capital F and the invariant Fx, and maybe not. I mean, this has never been seen before. But one thing is 100%, and that is that the obstruction that has been raised by Ornstein and Weiss is not going to matter. And the reason it's not going to matter is because the partitions are restricted to being generating partitions. And of course, the restriction to generating partition eliminates the issue of monotonicity, since by definition, partitions lifted from a proper factor space cannot be generating. So if you're going to define anything using generating partitions only, this obstruction is going to be avoided. Of course, the question is, if you define something by these generating partitions, what do you do with it? And so Bowen really has taken a really big step to develop entropy theory beyond a amenable group, and he proved a number of remarkable results for this new invariant, including the fact that it gives the right value for Bernoulli actions and classifies their isomorphism classes, which was a really remarkable breakthrough. And furthermore, he went considerably beyond that, and he defined another concept called the Sophic entropy for actions of Sophic groups, and established that it classifies their Bernoulli actions, which constitute a vast generalization of the celebrated theorem by Ornstein. We're not going to say much about Sophic entropy. This is a whole other subject. We'll only remark that the class of countable Sophic groups is truly extensive and may in fact equal the class of all countable groups. But this has not been settled yet. Some people are very skeptical about it, but it really does encompass a vast class of groups, residually finite groups and linear groups and hyperbolic groups and many, many others. So this is just really the bare just bare mention of this remarkable development by Bowen. But what I would like to do now is pass over to another remarkable development, a major breakthrough, which was initiated shortly afterwards by Brandon Seward. And Seward starts with a classical result of Rokhlin, proved in 1967, which asserts that the Kolmogorov-Sinai entropy for Z actions is equal to the infimum of the Shannon entropy of partitions HP, where P is a countable generating partitions of X. This is a classical theorem. It was proved, already in the 60s. You simply compute the Shannon entropy of all generating partitions and you take the infimum. And Seward and Tucker-Drob proved that this formula still holds for free ergodic actions of general amenable groups. And it was proposed by Seward as a general definition of an isomorphism invariant entropy for probability measure preserving actions of all countable groups, which Seward termed Rokhlin entropy. Now, this definition is really I find it really striking. You can define this notion of entropy in a first-year course in probability as soon as you define the concept of a Shannon entropy. It's quite remarkable on a number of ways. First of all, there's no issue in establishing that it's an isomorphism invariant. It's absolutely 100% obvious, because isomorphic actions have exactly the same generating partitions. So whatever it is, it's an isomorphism invariant of group actions. It's also remarkable for the fact that it's a very static definition. This definition has no dynamics in it whatsoever. It simply computes the value of the Shannon entropy. The only mention or the only hint for the existence of a group action gamma is in the concept of a generating partition. So this is really a very different philosophy, but nevertheless, it's an isomorphism invariant, which Seward has analyzed vigorously. So the question is, okay, what can you do with this invariant and what can you show about it? And Seward proved a number of remarkable results connected to it, various theorems of Krieger type, but I want to focus on one result, which is very striking and will be the key to our observations on this topic. One can define, I think this is also fairly classical, but I'm not sure exactly how to attribute it. So one can define the finitary entropy of a partition as follows. We let fin gamma denote the set of all finite non-empty subsets of gamma. And we can define HP fin is simply the infimum over all finite sets of the refinement of P with respect to the finite set divided by the number of its elements. And having done that, we can take once again, following the suggestion by Seward, the infimum over all countable generating partitions of this finitary entropy of the partition. And Seward proved the following remarkable inequality between Rokhlin and finitary entropy. Namely, for every generating partition P, the Rokhlin entropy is less than or equal than the finitary entropy. And from that, it follows immediately, simply by taking the Shannon entropy, that H fin, the finitary entropy of an action, is equal to the Rokhlin entropy of an action. So this follows immediately from Seward's inequality, which is really a very remarkable, it's one of the remarkable results that he established for Rokhlin entropy. And this result really is going to be a key to our own observations. And so it's time for us to discuss what we would like to discuss, which is convergence of entropy along almost geodesics in negatively curved groups. So let us go quickly over the various ingredients of this setup. So let M be a closed Riemannian manifold of strict negative curvature, gamma its fundamental group, and M tilde its universal cover. And SM will be the unit tangent bundle, SM tilde its universal cover, and GT from SM to SM and GT tilde from SM tilde to SM tilde denote the geodesic flow. And we denote by dm tilde the boundary of M tilde. And in addition, we fix an origin O in M tilde and let's say a Dirichlet fundamental domain D tilde in M tilde. And so there's no reason, and this is certainly interesting enough, to think about, for example, a uniform lattice in the group SL2R, namely a surface group. We have M, which is nothing other than the hyperbolic plane. We have a nice Dirichlet fundamental domain for our surface groups, which is a very nice polygon. And this setup, which we might keep in mind, is certainly the model for what we have in mind here, and certainly a case which is interesting enough. And we let nu denote the unique invariant measure of maximal entropy for the geodesic flow on the unit tangent bundle, and eta denote the Patterson-Sullivan measure on the boundary dm tilde associated with the origin. So this measure, of course, gives rise to the Patterson-Sullivan measure class. And now we would like to consider geodesics in M. And so each point P tilde V in SM tilde determines a unique B-infinite geodesic starting at P tilde in M tilde with V some direction which can be parametrized by the sphere at infinity dm tilde. And note that the set P tilde V, where P tilde is in the fundamental domain D tilde, can be identified one-to-one with SM, the unit tangent bundle. So I've decided to keep the notation P tilde in D tilde, namely work in the universe in the upper half plane rather than in the unit tangent bundle, but this is really just a matter of notation. And now, as is well known, for t goes to infinity, G tilde t acting on P tilde converges to a point in the boundary dm tilde. And along the way, the one-sided geodesic G tilde P tilde passes through a sequence of translates, gamma k D tilde of the fundamental domain. So the picture we have here is very geometric. We tile the, let's say, hyperbolic plane by our nice polygon, and we have a certain point in the upper half plane, and we have a B-infinite geodesic passing through it with tangent direction V at P. And of course, this geodesic is going to converge to infinity, and it's going to pass through a sequence of tiles in the tiling, namely sequence of translates of the fundamental domain. Okay, and now for t greater or equal than 0 and a point P tilde V in D tilde, we define an element of gamma. Gamma which is really gamma depending on T and P tilde V, via the equation that G tilde P tilde is in gamma inverse D tilde. So namely, that means that gamma K, it should be, gamma N PV returns the point Gn tilde Pn, Gn tilde N P tilde to the fundamental domain. And this is again a well-known construction. And so having done that, we are going to now define for a given P tilde and V in Sm tilde a finite set. And that is the finite sets gamma 1 PV inverse, gamma 2 PV inverse, gamma N inverse. This set of elements is simply the elements that we read as the label of the translated fundamental domains as we consider this geodesic and go to infinity. It's simply this sequence of labels that of fundamental domains that we see along the geodesics at time 1, time 2, time n. And so as a result, Fn P tilde V is an almost geodesic segment in gamma, starting at E. With respect to the metric on gamma, which is inherited from the embedding of gamma goes to gamma times naught in the universal cover. Okay, so the gist of what I've said now is that we have constructed a large collection of almost geodesic segments in gamma, which increase with n. And they are parametrized by points P tilde V in the fundamental domain, in the unit tangent bundle. In the unit tangent bundle equated with the corresponding set in the unit tangent bundle over the fundamental domain. And now, let X mu be a probability measure preserving ergodic action of gamma, and P a countable partition with finite Shannon entropy. And then we can consider the refined partition, well defined for almost every P tilde V, where we take our partition P and we refine it by that set, FNPV, a finite set. In fact, not just a finite set, but a nice, almost geodesic segment. So we refine the partition along this almost geodesic, where this family of almost geodesic segments is a measurable family with a measurable parameter, P tilde V, ranging on the unit tangent bundle. And of course, we can consider also the associated information function, namely minus log of the measure of the atom containing X in this refined partition. And so what we've done here, we started our discussion in a very deterministic fashion. We considered finite sets in our group G or gamma. At first, the group gamma was amenable, and we certainly have after the developments in this theory, nice deterministic asymptotically invariant sets for which we can assert convergence of entropy and convergence of information function. We're changing this. We are taking finite sets.
Amos, can I ask you a question for a second? Why are you saying that it's well defined almost everywhere? Isn't it defined everywhere? What's the issue with?
Well, the issue is that you can have a geodesic that traverses the boundary between two tiles. And so you're going to have to decide which one does it belong to.
Well, you've chosen the fundamental domain at the beginning of the discussion, right?
Well, okay.
I mean, you could just choose a measurable fundamental.
Yes, if you choose a measurable fundamental domain, then yes, it's true.
Okay, and the second question is the FNs you're considering, there often will be repetitions, right? So
there's going to be repetition. This is going to come into play. Yes, I mean, really, what I would like to do is go along the geodesic sufficiently fast. In other words, if the diameter of the fundamental domain is a certain c, then really I want to take steps of size, I don't know, 2c along the geodesic. And then I will guarantee that I move from tile to tile. And so I'm going to have n points in Fn, generically. Okay. Yeah, but it is true that if I'm going to go along the geodesic very slowly, then, I mean, I'm going to have a very small step and the diameter is large, then, you know, maybe the first 100 elements that I read along the geodesics are really one and the same. So does this answer the question? Barak? Hello? Shall I continue?
Yes. Thank you very much. It answers the question. But okay. Another question: Are your fundamental domains compact? I mean, is gamma co-compact?
Yeah. I mean, it's a closed surface.
Okay.
Yeah, right. I want to keep this sort of nice geometric setup for a while. Again, I mean, this can be generalized, but let's think now about a compact fundamental domain. Yeah.
Okay, thanks.
Okay, so now we can state the following convergence result for almost every geodesic. The first is Theorem A, that the following limit exists for almost every PV. For mu almost every x in x, it's the limit in these two measurable variables, PV in the unit tangent bundle and x, and I have the information function. And I have convergence in both almost surely in both variables. And the value of the limit is, in fact, nu times mu almost surely constant. And this constant we will denote by HPX. And it is given, in fact, by the conditional entropy. HPX is the conditional entropy of the partition P when projected on the infinite join along this entire almost geodesic. Namely, we consider the refinement from k goes to 1 up to infinity over the sets fk1 PV, which are fk PV minus the identity. So we have this convergence in both measurable variables, and we also have a formula for this limit. So this is the first part. Now, convergence holds also in the L1 norm. And so, in particular, for nu almost all PV, the partitions refined along the almost geodesic segments, FNPV, satisfies that the Shannon entropy, the average of the Shannon entropy, is, well, it converges, which is this integral that we have right here. Okay, well, I'm not saying this correctly. So what we have in the second line is a double integral, is the integral over the unit tangent bundle as well as over x, which is what you get, which is how you get the Shannon entropy. And so this double integral is, its limit is what we defined HPX, and also you can view it as the almost sure limit in the variable PV. Okay, this may be, okay, I will explain in a minute why I put in the double integral here. And another point which is significant is that if you consider the set Fp tilde V, which is the union over n greater or equal to 0 of Fn PV, well, that's a one-sided C almost geodesics in gamma O, namely in the orbit of O under gamma in the upper half plane or in the universal cover. And this is within C of a certain geodesic in M tilde, one-sided geodesic. And so we can denote the limit point of the corresponding geodesics in the boundary, the limit point in the boundary by F plus associated with PV. And then the law of this point is the Patterson-Sullivan measure class on the boundary. Okay, so this explains a little bit about the law of these limit points of this random this ergodic process. Okay, so this is the first part, and now we would like to define what we call the orbital Rokhlin entropy. And here we would like to assume that the gamma action is free, and also that the points that Barak mentioned a little bit earlier, namely gamma k PV. So the points we read, the group elements gamma that we read as the geodesics traverses the upper half plane and crosses these various tiles, these various translates of the fundamental domain, we want to assume that they're distinct generically. For that, we may have to adjust the speed in which we go along the geodesic. Now, under these assumptions, let's define the orbital Rokhlin entropy of x mu. So it's what we have established already as the limit of our process, hpx, and we take the infimum over the generating partitions of x, which, of course, I hope at this point has a very good motivation. And so the second theorem is that this definition of entropy is in fact nothing other than the Rokhlin entropy, which is the same thing as the finitary entropy. In other words, if we go back for a moment, what you have here, where is it? What you have here in the statement of Theorem A, okay, I think it's fair to say that this is a dynamical process. You go along geodesics in your nice negatively curved group, and you refine partitions in a general ergodic actions. And it turns out that for almost every geodesic, you will have convergence in both variables. It's fair to call this a dynamical process. And it turns out that this dynamical process actually, if you were to take the infimum over all generating partitions, it gives you the isomorphism invariant, which is called the Rokhlin entropy, defined by Seward, which was defined, as we mentioned, very statically as the infimum over the values of the Shannon entropy. And so the import of this program, of these statements, is that you have, if you like, a dynamical approximation to the Rokhlin entropy. So as a corollary, this is just saying again what I just said now. It's an obvious corollary that for every epsilon greater than 0, there exists a generating partition P epsilon such that the Rokhlin entropy has the following dynamical approximation. Nu times mu almost surely. The Rokhlin entropy is between the limit, the limit of the dynamical process P epsilon Fn PV is between the Rokhlin entropy and the Rokhlin entropy plus epsilon. This is a dynamic approximation to the Rokhlin entropy. And now, one thing that is very important to stress is that the value of HPX really depends on many, many choices that we've made in order to construct this limit. But the corollary implies that the orbital Rokhlin entropy is independent of these choices. It coincides with the isomorphism invariant given by the Rokhlin entropy. So there is an enormous flexibility in choosing these dynamical processes that will give you a Shannon-McMillan-Breiman theorem in the limit, but it's natural in the sense that the infimum over generating partitions will always give you the same Rokhlin and the same isomorphism invariant. So let me say a few things about the method of proof. I still have, I think, maybe 4 minutes. So in general, I should say that the statements I just made, they're really more observations than anything else. And the hard work here, really, I would say the most significant part of the hard work is carried by Seward's inequality. But first, Theorem A is a modest contribution to the theory of skew extensions of probability measure preserving flow using a measurable group valued cocycle, which of course is a theory which has long tradition in ergodic theory and entropy. The convergence of the double integral, namely the double integral over X and over the unit tangent bundle, the integrated information functions, was established by Abramov-Rokhlin already in 1966 in their theory of skew products, and by Ward and Zhang in 1992 for amenable groups. And pointwise convergence of the information function, namely some version of the Shannon-McMillan-Breiman theorem, was established for independent random transformations by Kiefer in 1986, Le Drapier-Young in 1988, and Bogenschutz in 1992, and more generally by Morita in 1986 and Zhu in 2008. Notice that this entire set of results about the so-called relative or fiber-wise entropy of a skew product over the base is defined by the authors mentioned above as the supremum over the finite partition P of X, the supremum of the fiber-wise entropy HPX that we saw above. This, of course, follows the classical Kolmogorov-Sinai definition of entropy in the case of a skew product. But given these new developments, it becomes very natural to consider the infimum over generating partitions of this fiber-wise entropy, and that is really the right Shannon-McMillan-Breiman theorem in this case of non-amenable groups. And so in general, one can say that Theorem A utilizes the methods developed in the context of skew products, and it establishes pointwise almost sure convergence for information functions in somewhat greater generality using somewhat sharper maximal inequalities. But yeah, it definitely uses some really well-established principles. Now, about Theorem B. Theorem B is a consequence of Seward's inequality. Indeed, if you go back to Seward's inequality, supposing that one finds any collection whatsoever, Fn, of increasing finite subsets of gamma, such that the entropy of the refined partitions, Pfn, which is the join over gamma in Fn of gamma P, converges. Supposing you were able to do this for whatever reason, then Seward's inequality implies that the infimum of entropy over generating partitions is equal to the Rokhlin entropy of the action. There's only one little problem, which is how do you find such finite sets in a general group? And in general, nothing is known about the existence of a deterministic sequence of finite sets Fn with this property when the group is non-amenable. I'm not aware of even one single example. So our approach is based on constructing explicitly and geometrically a measurable family of finite sets, namely none other than almost geodesic segments, which has favorable convergence properties almost surely. And once we have constructed that, you can take this measurable family of finite sets and you can put it into Seward's inequality and conclude that the infimum over generated partitions will give you the Rokhlin entropy. So you will have convergence, a Shannon-McMillan-Breiman theorem, which approximates the Rokhlin entropy. Okay, and so I have I started 5 minutes late, so I'm going to just add one last slide. And so one thing I should say is that similar results apply to all word hyperbolic groups. The geodesic flow on the unit tangent bundle of a negatively curved manifold can be replaced by the construction of a measurable geodesic flow for general hyperbolic groups. And the Shannon-McMillan-Breiman theorem for convergence along almost geodesic segments in this case relies on some recent results developed by Bader and Fuhrman. And now let me call your attention to the fact that this construction, namely, simply almost geodesics in a hyperbolic group or uniform lattice, it has very nice ergodic properties, at least as far as entropy theory is concerned. But, okay, so this variable measurable family of finite sets in gamma certainly has good ergodic properties as far as entropy equipartition is concerned. But in fact, in every ergodic action of gamma, these are very good sets. And averaging on these finite sets will give rise to a mean, maximal, and pointwise theorems. Among others, this can be developed much more extensively, and these would give rise to almost sure theorem. And this fact is a consequence of the theory which was developed in much greater generality in previous work with Lewis Bowen, which has to do with sets which are constructed as the image of a virtual homomorphism, namely the image of a measurable cocycle from an amenable ergodic equivalence relation into gamma. In this particular case that we're discussing right now, it is a consequence of the theory of skew product extensions. Okay, so yes, and so maybe the last thing I'm going to say is that Theorem A has a more general abstract formulation which applies to all countable groups. And here the measurable family of finite sets arises via a virtual homomorphism from a probability measure preserving amenable equivalence relation R on a probability space into gamma. Or equivalently, F and Y are the images under a measurable cocycle from this equivalence relation, amenable equivalence relation R to gamma, and they constitute the image under alpha of the sequence of finite equivalence classes of a hyperfinite exhaustion, Rn of R. For the case of entropy convergence, this result was established in previous joint work with Pogorzelski. Okay, well, thank you very much for your patience. And if there are any questions, I'll be happy to answer. And I'd like to thank the organizers again for this opportunity to speak in Dani's conference.
Thank you very much for the talk. Are there any comments or questions?
I have another question, Amos. So almost every set you have in the case you described, in the case of the unit tangent bundle on a compact surface, is it explicit? I mean, do we know what the geodesics are doing in order to satisfy the conclusion?
Well,
Yes.
I mean, the construction is simply that you take a point. Let's work again in the universal cover. You take a point, you look at the one-sided geodesic, and then you read the group elements that the geodesic encounters along the translates. That's the recipe.
Yeah, I understand.
So it's as explicit as you can make that process.
I'm asking, then you have to take a set of full measure in the unit tangent bundle for this to work. So I'm asking, can you explicitly describe this set of full measure? For example, if you know that the geodesic in the unit tangent bundle is equidistributing, does that imply that you can use it in your, plug it into your...
okay. That's a very good question. That's a very good question. And I have to admit that this is, at this stage, 100% almost sure theory. In other words, I cannot give you an explicit, which is, I understand your question, finite set, a sequence of finite sets with n elements in the group, such that they will average nicely, or they will refine partitions nicely in a general ergodic action of the group. That would be a very nice thing to do, but we are not able to do this. This is 100% a measurable result. I can tell you that almost every geodesic does that, but I can't tell you that I can find a geodesic that will do this for every ergodic action explicitly. So your suggestion is very interesting. Maybe if the geodesics has particularly good, ergodic properties in the unit tangent bundle, but we haven't looked into this, and the theory we've developed is a measurable theory. It's, I cannot deduce from this, we haven't, in our method, we do not have a natural way to deduce a finite explicit collection or a sequence of finite sets explicitly like that. Yeah, that's a very good question.
Okay.
So
thank you.
this is, this is a weakness of this approach, but this approach produces almost sure convergence. It produces convergence for almost every point, but it's not explicit, just like in the ergodic theorem.
Thank you. Are there further questions?
Yeah, hello, Amos. I'd like to know, given Fn, is there a partition giving the infimum, and can you say something about it? And does it depend on Fn or?
Well, I would say that since Seward has sort of brought this to the fore, the set of generating partitions of a given action has become really, I don't know. I think it's become one of the most interesting issues. I don't know if it received so much attention in the past, but now it's become one of the most interesting subjects. But not much is known about it. It would be great to have, like you say, to have the infimum be realized, to have some criterion, when does that happen? That would be great. But as far as I know, there's no result along these lines. The set of generating partitions is very mysterious. One would hope to be able to parse them a little bit. Maybe some of them are better than others, but all of this remains to be done. I don't know of any results of this type.
Are there further questions or comments? Yeah, if this is not the case, then let's thank the speaker again.
Thank you very much for your attention.